Let's go on with our discussion on decision trees. We have seen the pruning method, and now we are coming back to our baseball example. And we first divided the data set in two parts, leaving 132 observations in the training set and 131 observations for the test set. Then a large regression tree was built on the training data, and alpha, the penalty on complexity, the coefficient that controls the penalty on complexity, was varied in order to create subtrees with different number of terminal nodes, so trees of different complexity. Of course, now we have to decide what's the best complexity, and this was done by six-fold cross-validation in order to estimate the cross-validated mean squared error of the trees as a function of alpha. And the results are summarized here for the tree. So you can see first split number of years in the league, then we have the number of hits, and okay, and we can go out with our split and arrive at the high complexity tree. And here we have a summary of the performance, and we are looking at the training, the cross-validation, and the test. Remember that we have about half of the data that were not used for training, but were kept apart, and so that we can use them for a final test. All right, you can see in black, okay, these are the training means, these are the training mean squared errors, and they are plotted as a function of the tree size, so the number of regions. Okay, and okay, you can see, as expected, that the training error is going to decrease when I increase the complexity of my tree. So more degrees of freedom, I can follow better the training data, and therefore the mean squared error is going down. But this is not informative, so it will be better for me to have an independent idea of the value of the different trees, and this can be done by cross-validation. So when I perform cross-validation, I find that the mean squared error is greater than the one that I found in training, and this is not surprising. And the nice feature here is that at some point you have an increase in the cross-validated mean squared error. This means that there is an optimal size for the tree, which in this case seems to be 3. All right, so this could be the size that I'm going to choose. And finally, I can look at what happens on the test data, and I see that the performance on the test data is not far from the cross-validated one, so I have no surprises. Although you can see here that the performances of trees of different sizes is not going to change much, and it even happens that in the end it seems better to have a high complexity tree, but beware of the uncertainty. So here you have error bars, and of course this is going to warn you about the fact that there is some uncertainty in our assessments. Okay, and that's it. So far, we have been discussing regression trees, but the method can as well be applied to classification. It is not difficult to extend it to classification. Now you are going to predict a qualitative response rather than a quantitative one, and the prediction once you have completed your split, the prediction is made predicting that each observation will belong to the most commonly occurring class of training observations in the region to which it belongs. So rather than taking an average, we are just having a look at how frequently the different classes occur, and we select just the most commonly occurring. So once we have the split, it is easy to have the classifier. Some more details. Just as we did for regression, we use recursive binary splitting. And in the classification setting, of course, we cannot use RSS, the residual sum of squares, as a criterion. A natural alternative is the classification error rate. And this is simply defined as the fraction of training observation in a given region that do not belong to the most common class. So the definition is 1 minus max with respect to k, where k is the kth class, of p hat mk, and p hat mk is the proportion of training observations in the mth region that are from the kth class. So the ideal case is that in the given region, in the mth region, all the training data belong to the same class. In that case, this proportion p hat would be equal to 1. So this would be, as they say, a pure class, a pure region. So if you have a pure region where all the training data belong to the same class, then p hat is equal to 1, and 1 minus 1 is equal to 0. So you have zero error. Of course, this will not be the case most frequently, and p hat will be lower than 1, and if it is very small, then e gets quite large. Okay, so this is the classification error rate. This seems a good idea, but as a matter of fact, it doesn't work as well as other criteria. So there are two other measures that are more popular than the classification error rate, and one of these two is the so-called Gini index, that is defined in this way. This is can be considered a measure of total variance across the k classes, because you have a sum over k, of course, and you have p hat mk times 1 minus p hat mk. This is very similar to the variance of a Bernoulli variable, the same formula. And the idea is that this product is equal to 0 when either p hat mk is equal to 1 or is equal to 0. So if within your region all the classes are close, all but one, of course, are close to 0, and only one is close to 1 with their p hat mk, then you will have a very small Gini index, and for this reason, this index is referred to as a measure of node purity. So a small value indicates that there is a dominant class within the region, and it is the class whose p hat mk is close to 1 or equal to 1, while all the other classes have values of p hat mk that are close to 0. In this case, you can well say that you have a kind of pure region, because in that region there is a single class that dominates over the others. An alternative to this index is cross entropy, which is given by this other definition. So in this case, you have minus, and then you have the sum of the p hat log p hat. It turns out that though different, they have quite they work in a quite a similar way. So you can refer to one of these two indexes when you are growing your tree, and we illustrate the use of trees for classification by some data. These are heart data. They contain a binary response, a binary outcome, heart disease, whether the subject has a heart disease or not, for 303 patients that had chest pain, okay? And an outcome of yes indicates the presence of heart disease, and no means that there is no heart disease. And there are 13 predictors, including age, sex, in the sense of gender, cholesterol, and other measurements. We have been using cross-validation, and this yielded a tree with 6 terminal nodes. Let's see the figure. All right. So this was a tree with a high complexity tree. You can start from this, okay, and proceed with pruning. After pruning, you get this one that seems nice because the complexity is moderate. You can also have a simple explanation in terms of rules. So each split corresponds to a rule. And here you have the comparison between training, cross-validation, and the test in terms of classification error rate. So this is between 0 and 1. You can see again that the training goes down. Okay. As a matter of fact, this measurements was done in somehow similarly to cross-validation. So once you have trained your tree of some complexity, then its error on training data was computed on the faults used for cross-validation. In this way, by computing on the faults used for cross-validation, you can have a measure of variability, and this is how you can put error bars here. And you can see, therefore, that there is some oscillations, and also it is not monotonic. Okay, that is due to the variability that you have when you choose the faults over which you are assessing your classification error. And you can see that cross-validation and test are quite similar. Okay. You should look at cross-validation for the choice. We have already anticipated that 6 was the best, the smallest, the best complexity that was chosen. Okay, and you can see that as a matter of fact, in cross-validation, 6 has the best performance. Okay, so this is an example of how you could apply. Here there is a funny detail that I'm going to make you observe. Okay, here you have a split where both the leaves are no and no. How can it be? Well, as a matter of fact, if you are using the Gini index, it happens that you could split in such a way that you have no and no in both leaves. This is something that could happen. Okay. And so, of course, that is not giving a difference for the prediction. Okay. So those leaves give the same prediction. Okay. A comment about trees versus linear classification boundaries. So I'm thinking about discriminant analysis, for instance. Okay, And what are the pros and cons of trees? Well, it depends. If the original problem had a decision boundary, a natural decision boundary that was linear or not. So let's imagine that my my problem has a natural decision boundary, meaning that this is the optimal decision boundary, okay? For some reason we don't know why. And we don't know that this is linear, otherwise we wouldn't use decision trees. We approach the problem by decision trees, and then what will what is going to happen? We will possibly obtain something like this. So my decision trees partitions the predictor space in this way, and so this rectangle is yellow, this one is green, yellow, green, yellow, green. So it tries to approximate the linear decision boundaries by means of these boxes. Okay, this is not really very efficient, of course, because if you knew a line would have done the job, but in some way it succeeds at giving a kind of approximation. On the other hand, let's assume that the ground truth is of this type. So we have a decision boundary of this type with the green region with this strange shape and the yellow region that is just a square. In this case, you would be in trouble using a linear decision boundary. But if you are adopting decision trees, it will be quite easy to end up with a solution like this. Okay, so the idea is that there is no all-purpose method. So we should have a number of methods in our toolbox, and then, depending on the problem, use one method or another, or apply more than one method, and understand by the results if it was the correct one for the problem at hand. Okay, so some advantages and disadvantages of trees. As I said, they are very easy to explain, even easier than linear regression. Some people believe that they mirror closely human decision making. So human decision making is often based on rules, and therefore they could be more close to human reasoning than other regression and classification approaches. They can be displayed graphically and are easily interpreted by a non-expert, especially if they are small, of course. If you have a very large tree, that could be difficult to understand. They can handle quite easily also qualitative predictors without introducing dummy variables, and a trick that we had to learn with reference to linear regression. Unfortunately, they don't have the same level of accuracy, of predictive accuracy, as other regression and classification approaches. But as we are going to see, by putting together different decision trees, this predictive performance can be substantially improved at the cost of losing, however, the ease of interpretation and communication. Okay. At this point, we can introduce one of these methods that goes under the name of bugging or bootstrap aggregation. And this is a method of the general purpose method for reducing the variance of statistical learning. We introduce it here, speaking of trees, because it is very useful in this context, but it could be applied more generally. And the starting point is the well-known fact that given a set of independent random variables, each with variance sigma square, if I consider the average of these random variables, the variance of the average is given by sigma square over n. This is something you know very well. So if you are averaging independent observations, this is going to reduce their variance. Of course, this would be very nice if we just had if we just had multiple training sets, something that we don't have, of course. So, okay, good idea, but how could I apply it in practice? And here there is the key point. And if I don't have multiple training sets, I can produce them, and I can produce them by Bootstrap. Okay, so I just take the original data set and I generate bootstrapped datasets. You know that Bootstrap has to do with sampling with replacement from the given dataset. So in this way, I will generate capital B bootstrapped datasets, and then I will train my tree on each of these bootstrapped dataset and get predictions that we call f hat star b for a point x from each of my predictors. So it is like I had multiple training sets at this point. And then I take the average of these predictions. Okay, it is brilliant in some sense, but there is a point. Is it going to work? I'm asking this because when you are performing bootstrapping, your bootstrapped datasets are not independent. I started with the fact that the average of independent observations has a smaller variance. Okay, but if the observations are not independent, this is not guaranteed, or at least it is not guaranteed that the variance will go down as 1 over n. Okay, and so it could seem that it is not guaranteed that bagging is going to produce good results, but as a matter of fact, it seems to work. And okay, we can apply bagging to regression trees, but we can apply it also to classification trees. In this case, in order to decide what is the prediction for a new test observation, I will take a majority vote. So I have capital B classifiers, I will apply all of them, and then consider their outcomes as votes and decide in favor of the class that gets the larger number of votes. I can do bagging on the hard data, and this is the result. Here you already see results also for random forest. That is a method we will discuss in the next lecture. And here you have the result that you would obtain by a simple decision tree, which is the dashed line. And then I am applying bagging, and this is the green line. And this is an assessment of the performance made by out of the bag method that I'm going to explain, and this is the result that I get on test data. So you can see that the improvement is quite marginal. This could be explained by what I was saying before, that the bootstrapped data sets are not independent. Okay. We go directly to out of bag error estimation, and how can I have an assessment the error, of the test error of a bagged model. And here there is a nice way to do that. Recall that bagging is based on bootstrapped datasets. Since you are sampling with replacement, when you obtain a bootstrapped dataset, you are not using all the data. And on the average, it can be shown, and well, we will see it in the next lecture, that each bagged, it's bootstrapped, it's bagged dataset makes use of about 2/3 of the observation. So there is 1/3 of the observation that is not used for the training of a bagged tree. And these observations that are not used are called out-of-bag observations. So the idea is that I could exploit the existence of these out-of-bag observations that have not been used as a way to assess the performance of my bagged tree. So I can train the bagged tree on the bootstrapped dataset and see its validation error on the out-of-bag observations. Okay, and so we can predict the response for the out observations using each of the trees in which that observation was out of bag, and this will yield about B/3 predictions for this observation that we can average. Okay, in this way, we have a kind of independent assessment. So I repeat, so we take the height observation, and it happens that many of the trees, many of the bagged trees will have not used this observation. So I can try to predict this observation by means of the trees that didn't use it, that are about to be capital B/3. So I try to predict this observation, and I average the error that I commit, and in this way I have a kind of cross-validation error that can be used, and that was shown in the figure, the green line, and here OOB means out of bag bagging. So it is the assessment by out of bag samples, out of bag observation. It is the assessment of the performance, and you can see that it is optimistic because the actual performance in test was the black one. Okay, that was quite close to the simple decision tree. Okay. Okay, I think we are done for today, and so we can stop here.